Hello, welcome to our talk on pioneering 0 days at Pwn2Own. So just a quick introduction into who we are. We're both members of NCC's exploit development group, McCaulay, Hudson, and Alex Plaskett. We're doing full-time vulnerability research and exploit development. And in this talk as well, we had some collaboration with the hardware security team as well, because we're both like very software orientated. So having the hardware skills is beneficial as well. So just if you're not familiar with the competition itself and what is Pwn2Own, it's a vulnerability research competition held by Trend Micro 0 Day Initiative. It happens on a yearly basis. There's different iterations now. There's the automotive category, the desktop category, mobile phone category, and so on. And the one we're talking about today is the automotive one. The goal is to compromise a number of targets which the 0 Day Initiative come up with, and the prize is based on the perceived level of difficulty for that target. So if ZDI think it's hard, then the prize money should be higher. And this isn't like any kind of like shady exploit selling or anything. It's just like giving the vulnerabilities to the vendors directly and the exploits to the vendors directly so they can fix the issues and improve their product as part of the Pwn2Own competition. So we actually went after 3 different devices at Pwn2Own Automotive, but the one we're talking to you today about is the Pioneer DMH. This is one device which is an aftermarket in-vehicle entertainment system, an IVI. It's not one which comes in a car to start off with. It's not like already in a car when it's manufactured. It's one which you would have to install. And it's a fairly standard IVI with things like Amazon Alexa, Apple CarPlay, Android Auto, and so on. Costs about £1,000 or $1,300. So when we do Pwn2Own, we kind of go through a very similar process with our research. We've kind of, over the years, we've kind of come up with this methodology of how we approach it and what we do. So the first kind of things which we try to do for the targets are to do some background research, like literature reviews, like looking at previous vulnerabilities, looking at publications, seeing what other people have found in these devices. If it exists, some devices there's been no previous research on, but lots of times you see similar things. Then secondary, we want to gain some kind of device visibility. We need to see, like, to be able to find vulnerabilities, we need to understand how it works. So things like getting the firmware, being able to reverse engineer the firmware, analyze the firmware, being able to debug the device, either like dynamically debug the device and look and see what, like how things work. And then finally, we move into like attack surface mapping. So we understand how, like what network services listen on the device, what the attack surface is to an attacker, and how we could possibly like go after these areas and what would be interesting. So this is the kind of initial exploration phase where we really trying to understand and gain as much knowledge about the target as possible. Then we move into the vulnerability R&D phase. So that's like the bug hunting, all your common techniques like reverse engineering, binary reverse engineering, code reviews, fuzzing. We tend to use all these techniques depending on what we're looking at, whether it's open source, whether it's closed source, and so on. And then we'll move into like the bug hunting. We've developed tooling like over the years, like fuzzing, automation, looking for like specific classes of vulnerability, which we can scale up and go after targets. And then finally, the exploit development phase. So this is interesting for things like Pwn2Own because, like if you just have a POC, it might not work on the day of the competition. It needs to be quite reliable. It needs to work within the constraints of the competition where you only have a limited number of attempts to actually do the competition. So we need to heavily test our exploits, package them up, and make sure they're reliable. And then finally, and get them ready to go. So with the Pioneer, one of the first things we did was we were trying to get access to the firmware image so we could analyze the firmware and we could see, we could look for vulnerabilities in it. But it turned out the device firmware, it was encrypted over the air updates. We could download them, but we couldn't decrypt them because we didn't have the crypto keys to decrypt the images. So what we did was we used we went after the eMMC, the embedded memory management controller chip, where the firmware is stored, and we basically took a hot air rework station and removed the BGA chip, desoldered it from the board, and so we could gain access to the data like that. So that's what it looks like before and then after we've removed the chip from the board. So once we've removed the chip from the board, we can place the BGA chip into a reader, into an eMMC reader, a socket reader, and we can just use LO setup to and dump the different partitions in the firmware. And this is a good start. We because we found out Pioneer hadn't encrypted their firmware at rest. There was no DM crypt or anything running, so we could access the file system and the binaries on there. The next thing we were looking for was we were trying to look for a way of doing debugging on the device at runtime. So one common way of doing this is looking for UART. It's just a simple universal asynchronous receiver/transmitter, two wires where you have the RX on one device connected to the TX on another device, and the TX and the RX connected. And that way, it often provides some kind of visibility of what the device is doing, whether that's like console output or possibly input. It varies depending on like the state of the device. Like in production, vendors have tried to often remove this debug capability because they don't want to ship this in production devices, but in development devices, it may still be there. But often it's possible to re-enable it as well. And it's really useful for doing like reconnaissance, analysis, and just generally seeing what's going on. So we looked at the FCC filings as well. This is like super useful for when you're doing any embedded device research, because you can often get access to the FCC filings before you have the physical device, or before you disassemble it and take it apart and understand what's in there, and you can identify the chips and so on. And we noticed when we looked up this device, we found internal photographs of a pre-production device. So this was quite cool because it showed there was a number of debug connectors on the pre-production device, which are highlighted in the red squares. And if you look on the one on the right on the production device, you can see that those connectors have been stripped off. It also said on the silk screen as well, it said debug serial. I was like, oh, that's pretty interesting. That's probably you, Adel. So being able to go back to the production device and probe around in those different locations to see if these are the likely places, then it could be there. So what we did was we basically just put the connectors back on again. So we bought some FPC 10-pin connectors, resoldered those to the production device, soldered it up, and we were like, okay, maybe we've got UART at this point, maybe we can get something working. But unfortunately, we didn't actually, nothing happened. So we're like, okay, well, why is this? So there's typically a couple of ways to disable UART. One is in software and one is in hardware. We decided to analyze this first from a software perspective. So looking through the different binaries which we'd extracted from the file system image from our initial chip off dump, we could see there was a hidden screen. There was essentially like a hidden key press, which you could do. You could touch source off and then go 31312 in a pattern on the screen, and it would pull up a debug menu. We're like, oh, this is quite cool. But it was asking for the debug password. At that point, we didn't have the debug password. We're like, what? Well, where could this be stored as well? So We did some more reverse engineering, and we found libphmi underscore plugin min, which is used for the I think it's the human machine interface. It's used for like the GUI interactions and so on. And it had some hard coded strings in there. One of the strings was dev debug on. I was like, oh, well, that's clearly like developer debug, like, yeah. But there was also a Posidon debug on as well. So you're like, okay, these sound like interesting strings. We'll try these as passwords. And we tried the Posidon debug on one, and it gave us access to the debug menus. So at this point we had the access to the debug menus. But me and McCaulay, we can't read Japanese. And the menus were English and Japanese. But luckily we've got Google Translator. So it's quite easy. We just run the Google image translation against the Japanese, names, and we can see, what they are. Now, like in this debug menu, then we found something which said debug serial output, which is pretty much exactly what we were looking for when we were we're trying to re-enable the serial line. So we just toggled this to it was in the state of being off. So we and the console input as well. So if you want to try like maybe gain a shell, maybe you could just turn the console input on and see what happens. So we turned both of those on to see what would happen. And we got a little bit further. We basically found the TX started working at this point. So the transmission from the device to the to our receiver, to our computer, was basically giving the boot logs at that point. And we could see the output from the bootloader and from the kernel booting, and how the hardware initializes and so on. But even though we turned the console input on, we weren't able to actually like see our key presses at all. And that's really what we were looking for as well. So we were like, okay, well, maybe they've done something in the hardware to actually stop the RX line from working. So what you can do is you can take like a USB serial UART adapter, connect the TX from that to a needle tip probe, and then basically just probe around on the board looking for where the RX could possibly be. And then at that point, if you see like your keystrokes being echoed back to you, then you know that you've found the input. And it's quite common that the device manufacturers, they'll try to do things like they'll break the traces on the PCB, or they'll remove resistors, just thinking it's like that's enough to like stop someone. But actually, on the back side of the board, when I was probing around, I basically could see that there was I could see my input being echoed back to me again, and that confirmed my assumption that there was either a broken trace or a missing 0-ohm resistor. So at that point, we're like, okay, well, do we have a shell at this point? Like, surely we've done quite a lot of work to get here. But we got to, we could see our input, and we could try log in now, which was progress. We could see that we could see the login prompt in the banner. But we didn't have the login password. So we went back to our firmware dump, and we got the etc shadow file, looked in there to see what users were enabled, and there was only one. It was the root password, and the root password hash was in there. So we took that password hash out. We ran it against our GPU cluster. We tried brute forcing 7 alphanumeric characters. We tried things like common password lists. We even tried like Greek methodology, because we could see that they liked things like Neptune and Posidon and things like that. Maybe they just like get lucky with that. But we didn't go much further with the brute forcing, because it gets kind of computationally costly when you try brute forcing over that approach. So our next thing to do was we we thought, okay, we'll take our dump, we'll patch a backdoor into the dump, into the file system, so we can basically place drop bear, like an SSH daemon onto the file system, and then we can reattach the flash and reattach it to the PCB, and have our backdoor run, because they didn't have any like DM Verity or anything like that, which would protect against this. So when we initially removed the BGA chip, we tried as hard as we could to keep the BGA balls intact, but we had to actually do some BGA reballing. We tried using a BGA stencil, but unfortunately that led our first device. We couldn't boot our first device. We don't know exactly what we killed on that, but our device wouldn't boot, unfortunately. However, we had a second device, so it wasn't game over. We could try a different approach. So the next thing we tried was in-circuit programming, and this is basically where you leave the eMMC chip on the PCB, and you try to program to that chip while it's still there. So if on the silk screen near the eMMC, they'd handily labeled the pins from the pads from MMC D0 to D7, which is the data lines for the chip, and the MMC CMD, which is the command line. But for some bizarre reason, they'd left off MMC clock, like the clock signal. And to do in-circuit programming, you need at the minimum D0, CMD, and the clock signal. So that was a little bit weird because they'd labeled the rest, but that one was missing. So I spent quite a long time probing around, looking at the different test pads with Logic Analyzer and trying to work out which could possibly look like a clock signal. But it turned out the clock signal was only exposed through a little tiny via, not actually like a test pad. It was like a via which goes through the PCB on the circuit board, which is really close to the MMC chip. And then attaching to that, you can basically use a fiberglass pencil, like rough up the via, and then you're able to solder onto the via and like interact with it. And at that point, we've identified the clock. Well, we can use our needle tip probes and Logic Analyzer to see if we've identified the right areas. And looking at this, looking at our capture from the Logic Analyzer, we can see that we've got what looks like valid eMMC specs happening, and we can see eMMC traffic and the clock signal and so on at the top, and it looks valid. So we're like, okay, we've got all the places. This is just what this looks like in our final setup with our probes and like breadboards and so on. So in summary, that was what we did was we soldered up a hardware we soldered up a connection so we could connect it to a hardware programmer. We used a microscope to connect to find the tiny via, solder to the via. But we had one problem, which was actually that if the SOC and the eMMC are on the same voltage rail, the same power rail, then when you're powering both will come up, and there'll be some contention from the SOC preventing reads and writes or disrupting them when you're trying to do it through an external reader. So what we did was we found N sys test pin on the board. We grounded that, and then that basically held the SOC in reset, and then there wasn't any contention happening. And but funnily enough, we found out there was also like a second another CPU on the board, which was acting as like a watchdog. And if we held the SOC in reset for too long, we'd get power cycled, and we would our reads and writes would get disrupted. But because we had a firmware dump, our initial firmware dump from the chip off, we knew the offsets in the flash, which we were looking to patch for etc/shadow, and we could just patch these within 5 seconds before the watchdog kicked in. We could have tried to maybe like cripple the watchdog, but we didn't know what was happening. So, so this is just the tooling which we used. We used XGECU reader, hardware programmer reader to do this, which gives ISP in-circuit programming capability. And that gave us a shell because we patched in we replaced the hash with a hash which we knew the password of, and now we've rooted it from a hardware perspective. But this is only stage one of our research. This is gaining the initial device visibility. This is not enough for Pwn2Own. This is just allowing us to find the vulnerabilities for Pwn2Own. I'm going to now hand over. I'll just do a quick summary of what that was. So we've got the. So we did the eMMC chip off to do a firmware dump. We identified UART. We resold some connectors. We accessed a hidden debug menu. We reverse engineered out a fixed password. We re-enabled some menus. We resoldered a broken trace, and we patched the shadow file using eMMC in circuit programming. I'll now hand over to McCaulay to talk about the software section and software exploits which we used.
Thank you, Alex. So as Alex mentioned, all that process that he just talked through for the hardware attacks wasn't actually allowed in the competition because hardware attacks themselves are not part of the competition. But they gave us that initial visibility of the device and the ability to reverse through the firmware and to have the debug capabilities so we could debug the various programs and things. And this helped us a lot with being able to find the vulnerabilities. The other competition rule for Pwn2Own is that the vulnerabilities that we find and use need to result in some form of code execution. And then what I'm going to cover is the bug we used. The main one was due to insecure HTTPS response handling. So essentially the device makes a HTTPS request, and we are able to intercept that in a way where we can choose the response, and the response allows us to do a chain of events which eventually leads us to code execution. So as a prerequisite for that, the very first thing we need to do is have a fake HTTPS server. And the way we can do that is we host a Wi-Fi hotspot, and then we get the infotainment system to connect to our Wi-Fi hotspot. And what that allows us to do is by being in control of that hotspot, we can control the DHCP server. And the DHCP server allows us to assign the infotainment system an IP address, but more importantly, it allows us to control the DNS IP address that is used on the infotainment system. And of course, in this scenario, we tell the infotainment system to use a DNS server of our choosing, which in this case is our laptop itself. So then any future DNS queries which are then received by our laptop, we can control. So any domains that it wants to know the IP address of, we can just resolve to whatever IP address we want to. And in this scenario, we resolve the IP addresses to our own attacking machine again. So we're essentially redirecting all this information through to our own machine. And what that ends up doing is when the device tries to perform a HTTPS request to, for example, api.sports.gracenote.com, instead of going to the real web server, it's getting trafficked through to our attacking laptop. And the other important thing is the code within the infotainment system. When it is performing the HTTPS requests, it's doing it insecurely with a curl flag. So it does not validate that the actual HTTPS remote server is who it genuinely says it is. And that allows us to just create a self-signed certificate on our laptop, and it will just accept that self-signed certificate as if we are this Gracenote server. Just a little bit background information on what Gracenote is. It's a third-party library relating to sports information. It's just lots of sports data, and that's the main service we're actually attacking. So the infotainment system has a companion mobile app called Car AV Assist, and the typical usage of this would be you'd have the app on your phone, and you'd configure various different things within the app, such as your favorite sports teams. And then what that would do is it would allow you to, in a normal scenario, have updates about your favorite sports team on the device. For example, if your sports team had a match today, it would tell you the score results or when the event's occurring, etc. And for this particular attack scenario, we just need to set up a favorite sports team, for example, a football team, on that app. And then on the infotainment system, we open the Car AV Assist app, and then we just perform a sync. And what this sync does is it copies that information from the mobile device to the infotainment system. So it's setting the favorite sports team onto the infotainment system. And then when you trigger this sync, that's what triggers this HTTPS request that we're attacking. So the very first HTTPS request that is sent from the infotainment system to our attacking controlled web server is just getting the sports events for the particular team ID. In this case, the team ID is just a football team, and it's just a random letters and numbers. And now, because we are the web server, we can respond with any response we want. But in the very first example, we're just responding with a fake sports event in order to trigger the device to keep making concurrent requests. So in this scenario, we just say there's a fake sports event, it's scheduled for tomorrow. So then what happens is it sends off the next request and says who's participating in this sports event. So it's wanting to find out what teams are involved. And we just respond with two teams. So the first one is the team that was the favorite, and the second one is just a fake fictional team that we can control. And now in the participant ID, which is actually the organization ID, we have a path traversal attack here, but it's not executed at this point in time on the device. This is just required for the further requests to eventually hit the trigger. So the participant ID is just a series of alphanumeric symbols, and it doesn't matter at the moment what that is. And then what it will continue to do is just keep sending requests and gathering more information about these teams and these organizations. And so the next request is just trying to find out the various different names for the organization ID. And again, we just use that same path traversal ID, which at the minute doesn't trigger anything, but just needs to match the previous requests in order to continue the flow. And then what happens is it tries to get the images or the image metadata for these two particular organizations. And as you can see, the first ID is the path traversal ID, and the second one is the favorite team. And this is an example response of a typical response which the actual Grace Note server would return. So you have the ID, you have the metadata such as the image width, the image height. You have a URL, which is just the URL to the image to download, in this case a team logo. And then you also have the entity ID, which is, again, something that we can control. And what actually happens in this case is it will make a subsequent request to this URL that we can control. It will download the file from that URL, and it will keep just the extension part of the URL, so in this case .png, and it will also take the entity ID, and it will save that image that has been downloaded to the disk. It'll save it as the entity, so gn3f.png, which is from the extension. And so because we can control these, we can actually do a path traversal here in order to write any file onto the system that we want. So this is the actual malicious version. We change the URL to the api.sports.gracenote.com domain, which is again going to be redirected to our laptop. And then the file is just payload.txt because there's no actual validation on the file name or the extension or actually even the file contents. So in this case, we've got a .txt file and the contents of which we can control, as it doesn't have to be an image, it can be anything. And then the entity ID is the one which you saw previously, which was the path traversal. And so what ends up happening here is it will download the payload.txt file from our laptop, and then it will save that to the pkcs11 file.txt on the file system at the given path. And this allows us essentially to write any file with any contents in any location on the infotainment system. So in this specific scenario, we're returning this contents to the payload.txt file. And this is actually a configuration file which we're overwriting within the web browser. So this infotainment system has a built-in web browser, and this pkcs11.txt file is a configuration file for the browser. And one of the parameters that you can configure in this configuration file is a library. And you can also pass the full file path to that library. And in this case, we're passing it to the USB file path. So we're going to load the library from the USB pen. Now, the actual decision of which file to target was quite difficult because the majority of the file systems were mounted as read-only. And with only the ability to write a file, we couldn't remount any of these file systems. We couldn't do anything other than target one which was writable. Another issue we came across was many of the file systems are mounted as no exec, which means the file path of the shared object is quite limited because it would not execute in any file path which was marked as no exec. And to begin with, we thought we would use a USB pen, and we tried a USB pen which was mounted as exFAT and as FAT32, but they were both mounted with the no exec flag. And then eventually we figured out to just mount it as NTFS, and it turns out that NTFS does not have no exec for some reason. And so we're able to use a USB pen with NTFS with the shared object on in order to for that configuration. And the other issue as well we had was because the mounted file systems were so limited, there was not actually many files we could overwrite. There was no shared objects we could overwrite. There was no binaries that we could overwrite. Nothing like a bash script, etc. It was just a very limited number of configuration files. And so our next problem for the competition was once you press sync and you start that exploitation chain, you can't then re-interact with the device. You're not allowed to manually reboot it. You're not allowed to manually restart the browser, for example. And now this is just a specific case for Pwn2Own. But we needed some method of rebooting the device in order to reboot the browser, because when the browser reboots, it will read that configuration file and then trigger the shared object. And so the way we did this for Pwn2Own is we fuzzed a different binary, which was called media. That listened on port 2000. And we just passed it this packet, and we don't know what this packet does, but we just know it crashes the media file and then causes the device to reboot. Again, we didn't really look into the specifics on what that bug was, if it was exploitable, etc., because for the competition, all we needed to do was just reboot the device. In terms of the actual shared object itself, again, as I mentioned, it's pointed to by the pkcs11.txt configuration file. It's stored on the USB pen, so we can fully control that shared object. We had to implement the shared object and build the shared object with the exported functions which are typically expected for the web browser. So we had to implement, for example, nsc get function list. But instead of the correct implementation, we just triggered the execute function, which just runs a system command. In this specific scenario, we're running the telnet server. So then once that's triggered and executed, it's running telnet on the infotainment system, and then we can just log in as the user. In this case, because the pkcs11.txt configuration file is read and executed by the web browser, we are logged in as the web browser user, which is netfront B. And all this was all we needed for the actual competition itself. So that was last year in Tokyo. And as you can see on the left, that was prior to the exploit. And then on the right-hand side, you can see the telnet shell afterwards. So as a summary for the software exploit, we initially triggered the Grace Note communication through the mobile app by syncing the sports team. That would send the request to our laptop, where we have a HTTPS server responding to those various HTTPS requests, one of which was the path traversal, which allows us to write a file on the infotainment system. We had the malicious shared object compiled and plugged in on a USB pen, which was formatted as NTFS. And then it overwrites the pkcs11.txt configuration file. Then we trigger the restart of the browser by sending that fuzzed packet. And that ultimately results in executing telnet, so then we can just telnet into the system. Now, obviously that just gives us a low privilege user, but this device had quite an old kernel version, so we just used a very common kernel exploit to become root. So then we were thinking, what could we do now we're root on this infotainment system? What impact does that have? We didn't spend a huge amount of time researching this, but it was very clear straight away that there was a lot of information on the infotainment system which you might not realize. So just by pairing the phone with Bluetooth, you can access all the contacts from your phone. You can see the call history, so who's been calling you and when. You can see the live GPS coordinates of the device, and that's continuous as well. So if you are continually pulling that GPS coordinate, you can just see exactly where that device is whenever. And then various other pieces of information, such as the browser cookies, your Wi-Fi username and password, background images, and so on. And so what we did is we just built this very small implant, which essentially just grabs all this information continuously and just exfiltrates it to a web server that we can control. And then we just display that information on the web server, so you can see the contacts, the call history. You can watch them with Google Maps and see the pin following them as they're driving down the road, as well as all the other information. There is other information which could be interesting to look at. For example, you can connect dash cams to this. You can connect a microphone. You can also connect some third-party integrations within the vehicle, and presumably you can retrieve all that data as well and exfiltrate that data. So here's a demo of the exploit in progress. So at the moment, we have the web server running, and at the bottom you can see the actual device. And when we click that sync, you can see all those various HTTP requests happening, including the download of the pkcs11.txt file, and then obviously the reboot command at the end, which triggers the reboot of the device. And you can also see near the top the fake organization ID, which is the path traversal to that pkcs11.txt file. So after the device is rebooted, in a moment, that screen will disappear and then it will start the web browser. And now that the web browser's started, it will have executed that shared object from the USB pen, and then we have that telnet shell. So now we can just telnet into the infotainment system, and we have access as that NetFront B user. And then we just use that Linux privilege escalation to become root from the NetFront B user. And then we have the spyware app running. So this is the web server. And then we also have the implant running through Telnet. And then the implant will just continuously post all the information from that device to the web server, which then allows us to view the web server interface and obviously see all that information. So in terms of patches, we didn't know really when it was patched exactly because Pioneer never released an advisory, and we kept an eye on the patch notes every time they released a new patch, but we never noticed anything saying there was any security fixes. So we tested version 3.06, and it turns out we tested it through the dynamic testing because we didn't want to do all the dumping of the firmware again. And we noticed that the HTTPS was now being validated and verified correctly. So they are preventing that scenario of you hosting your own HTTPS server. But again, we don't know when this was patched exactly because they didn't release any notes in the change logs. So it was patched silently at some point. But we assume they've all been patched if this initial SSL one has been patched. However, we haven't been able to confirm that through the firmware itself. And then that's a list of the various CVEs. The first one was the improper certificate validation, which was definitely confirmed as being fixed. The second one was the path traversal, which has allowed us to write a file anywhere on the device. And then the third one was the denial of service for the media service, which was a fuzz packet, which causes the infotainment system to reboot. And we've confirmed that that third one's fixed, actually. That is all. Does anyone have any questions? And thank you for listening.
We got time for questions. Yes.
Hey, thank you for the great talk. So I was wondering, did you actually needed to root the device? I mean, get the shell from the hardware perspective to actually find all of those bugs and exploit them? That's my first question. And also I was wondering, you said that some of the mounts are no exec, but then you are copying the telnet to TMP and executing it. You couldn't do that with the lib and without using the pen drive?
Yeah, so I think we could have copied, so we could have iteratively reused that vulnerability in order to write the shared object to TMP and the .txt file. But for the competition, we just wanted a more reliable option of using the USB pen because that was allowed. But yeah, in reality, if you was to do this without the USB requirement, you could probably write to TMP. In fact, no, because you need that reboot as well. And the reboot will clear out TMP.
Makes sense.
So, yeah.
And what about not having the shell? Because I imagine that by doing the shell, you were able to easily find out what's running on it and how it's running and so on. But I guess you could find all of it without the shell, right?
Yeah. So
so I can probably, one hard part without having the shell would have been locating the PKCS 11.txt vulnerability. Like we could have done that probably from the firmware dump. But like I found that actually I found that like manually looking through the file system and looking at the process listing, and I tried to do things like enabling LD debugging, so I could basically see what shared objects were being loaded by each of the processes and so on. So yeah, it would have been possible, but I think it helped basically. Yeah.
Thank you.
Yeah, thank you.
Okay, so I've got a similar question because I thought how you found the vulnerability with HTTPS. So you've got root access and then what? Did you go like listing processes and go one by one, or you just tried doing like basic web exploitation, or how did you at end get?
Yeah, so we did a lot of techniques because we spent a lot of time researching lots of different binaries and such. So it's hard to remember. I think we was essentially reversing some of the main Pioneer custom binaries. And one of them which stuck out to us was telematics, because we was kind of looking as well as to see if they're exfiltrating any logs. And so if we make any crashes, we don't want it to send to Pioneer. And it was kind of, as we was looking at that, we saw the other functionality with the team. So we kind of started digging deeper into that as well. So it's kind of a bit of chance, but.
So about the logs, can't you like use your own DHCP to basically use your own DNS and block all of the communication?
Yeah, you can.
Okay.
But it depends, because sometimes you want the functionality to be able to talk to the actual servers in order to continue other things.
Right.
So in some cases, it's a bit.
Yeah, that's true. And my second question was, you said that there were cookies, and were they cookies from the Pioneer or the cookies from the phone you were syncing were also syncing?
So the cookies were part of the inbuilt web browser on the Pioneer device itself. So if you was logging in, for example, on the Pioneer itself, then the cookies from that web browser.
Yeah, so the cookies from your mobile phone wasn't synced?
No.
Oh.
From the mobile phone, it was just things like your contacts and your call history.
Yeah, great. Great talk.
Thank you.
Okay, first of all, it's great talk. It was really interesting. And my question was, at the beginning of the talk, you mentioned that the Pioneer device supported also like Android Auto and stuff. So this binary that had the path traversal vulnerability, etc., was it like a custom binary, or was it an Android Auto app? What kind of binary was it?
Yeah, this was just a normal ELF binary, not part of Android Auto. It was just, I think it seemed to be created by Pioneer, but we don't know for sure whether it was like a vulnerability with an SDK, because it was talking to Gracenote as the back-end server. We don't know if this it was an SDK which then integrated into their app. Maybe there's other devices out there which are using the SDK, but or it could be Pioneer code. We don't know for sure. So,
thank you.
Yeah.
All right. So thank you so much for your presentation. I saw that the type of communication that you used in your models were HTTP 1.1, right? And in case that you, for the other types of HTTP, for instance, HTTP 2, do you think you can still get the same results or not?
So I think it was do you mean in terms of the HTTPS traffic? I think it was so essentially what they was doing was they was using curl. But in curl, you can configure the SSL options, and by default, it's secure, but you can choose to have it insecure. So, for example, with the command line, it's dash insecure or -k. But this was using the curl shared library, of which they was turning the SSL verify to false. And now that it's patched, they've basically just flipped that to true. So I don't know if the actual HTTP protocol version matters. I don't think so. I think it was purely just on that curl option that they had configured.
Yeah, it's common to disable the certificate validation in development and then not re-enable it in production, forget to re-enable it in production again. So, and that's like a common way of that being, like skipping the verification checks.
Thank you very much for the talk. I have two small questions. The first is, how many people were you? Like, how many man hours was this?
So for this one, it was just us two. In terms of the amount of effort,
so for Pwn2Own, we did 3 devices this time around. So we did the Pioneer, the Alpine, and the Phoenix Contact Gyrex. We spent many months looking at all these devices, and we kind of prioritized what, when we'd finished with one device, we would kind of move on to the next one, and or parallelize our effort and so on. But yeah, I'd say maybe like 3 months, over a 3-month period on and off looking at other devices as well. So yeah.
And my second question is the hardware vulnerabilities. You mentioned like the eMMC not encrypted, or like those things. Did you also report those?
No. So, they're like, things like not having disk crypto, you could consider it a vulnerability, but it's kind of like a design choice as well. So it's, but there's definitely improvements which could be made on the hardware side from the hardware security perspective. Yeah.
Thank you.
Yeah.
And how much time did you have for an attempt of exploitation? And what would happen if, like, you would have an exploit that, would need to take longer?
Yeah, so for this one, it was 10 minutes per attempt, and I think you had 3 attempts maximum. And if you run out of time, that's your attempt done. So if you have a really long heap spraying exploit, for example, you just have to optimize it in a way to be less than 10 minutes, otherwise it's not going to be valid.
Does this mean that the vendors do not care?
No, so you can still report it after the fact, and it's just the prize money is way lower, or potentially nothing. It's just for the competition. That's the way they do it. But you can kind of play the odds. So, for example, if you know it's 33% chance if you do it under 10 minutes.
So the competition is not really like advertising for actually fixing the bugs. It's actually advertising for being the best hacker out there, kinda, and being able to write a proper exploit that would execute in minutes that could be used, for example, by state actors.
I think the timing constraint is put in because they don't want the competition to run forever. Like they want to.
I mean, it makes sense.
Yeah,
but, having an hour, for example, would make sense.
Currently, it's running over 3 or 4 days.
I mean, currently it's running over 3 or 4 days, which is quite a lot of effort for them to run. So, yeah.
I have maybe a similar question, kind of like a philosophical nature. Do you think that this kind of setup, like Pwn2Own, is beneficial for security in general? Because in the end, making like a full exploitation chain with privileged escalation, this is unnecessary for the vendor to fix the bug, right? So it's like you could report this immediately and not sit on the 0 day for months while it might be exploited, in the wild. You might actually report it immediately and then move on to searching for other bugs.
But I think it adds impact though, because a lot of vendors might just see it as another high which has no impact, because there's no proof that it can actually be done. They just see it as, well, we'll fix it when we can because nobody's done it. So I think it does help having the ability to show that you can actually leverage these, something that says like CVS 9.8 or even a 5.6, for example, to actually demonstrate some impact. So I think it's useful. I don't know if you can.
Yeah, I mean, I think it helps vendors prioritize which bugs are actually properly exploitable. You can look at bugs and you can be like, well, this is probably exploitable. We can fix this, but then there might be one which is definitely exploitable, and we could like prioritize that more. And also it helps vendors understand the mitigations as well better, because you can basically see when somebody goes to the full extent of putting an exploit chain in place, they can think of more strategic mitigations, which can break the whole chain, or they can close down entire classes of vulnerability, for example. So, yeah.
Yeah. Thanks for your talk. Since you mentioned that the device was running Linux, did you check if the vendor actually released the GPL source code? And if so, was it any help?
I'm trying to remember now for Pioneer.
I don't think they did. Yeah.
Quite a few of the vendors we looked at did release GPL, and it does help quite often. But I think for some reason, some vendors you have to specifically ask them if they'll release the code, and then they will, and they'll probably send you like an email and such. But for Pioneer, I don't recall.
Yeah, I mean, I think in this instance, like the GPL code would be the Linux kernel, and it wouldn't have helped us that much because with a privilege escalation which we exploited, like we could do that based on the version numbers itself. We could just be like, okay, well, it's vulnerable to that. We can try that out. So, it would have helped us maybe if we would have had to identify additional privilege escalations or things which Pioneer had specifically implemented into theirs to make it more vulnerable, like outside of core Linux. So, yeah. Thank you.
Time for coffee break. So thank you for this amazing talk.
Thank you.